Hello everyone, my name is Duy and today I want to present my study, which is about investigating experimentally and numerically chemical effects of ferrocene and 2-ethyl hexonitrate on a low-octane gasoline by a rapid compression machine. For decades, fuel additive has been used in conventional engines to get better engine performance. Cetane boosters are used to increase cetane number of diesel fuel. Octane boosters are employed in gasoline. Actually, engine researchers focus on developing engines operating at low temperature range to benefit from reduction of emissions. In these engines, control of fuel reactivity is the key element to ensure fuel engine adequacy. In this, use of additive is an efficient method to control fuel reactivity. General chemical effect of fuel additive has been identified in the literature. Some reactive compounds such as nitrates and peroxide are used as cetane boosters. These compounds contain weak chemical bonds which can break easily to produce free radical and increase radical pull. Conversely, octane boosters are used to decrease radical pull. Some efficient octane boosters are organometallic and aromatic amine. Kinetic models are crucial for engine development. Despite the general effect of fuel additive has been examined, kinetic models of fuel additive are not well developed in the literature. My study focused on ferrocene. Ferrocene has been proved as an efficient octane booster in the literature. Fernac and co-workers suppose the effect of ferrocene is an heterogeneous effect which relates to the deactivation of reactive radicals by the absorption of reactive species on the surface of iron oxide particle. The goal of this study is to contribute to the understanding of the chemical effect of ferrocene. To achieve this, we investigate the effect of ferrocene in a low-octane gasoline fuel in the condition of low-temperature combustion. The employed surrogate fuel contains N-heptene and toluene. This blend is an appropriate surrogate fuel for gasoline. Thanks to the validated sub-mechanism of ferrocene, we provide new insight into the different chemical effects between ferrocene and 2-ethyl hexonitrate, which is a conventional cetane booster. This additive has been previously studied in our last work. I present here the experimental method used in this study. We use a rapid compression machine to quantify the reactivity of fuel. I show here a typical pressure history during a rapid compression machine test. An experiment consists of two phases. The first phase is the compression phase. During this phase, the gas mixture is compressed to the desired condition thanks to the piston movement. Once the piston stops, the combustion phase starts. It takes a small time to observe a rapid increase in pressure. This time is defined as the ignition delay time. The reactivity of a fuel is represented by its ignition delay time, named as IDT. Under some conditions, two-stage ignition can occur. As you see here, the pressure rises a little bit by the first stage ignition and then rise remarkably by the main ignition. The neat surrogate fuel have a research octane number of 84. The doping level of ferrocene varies from 0.01 to 0.1 molar %. The experiment was conducted at 10 bar from 675 to near 1000 Kelvin for stoichiometric mixture and for lean mixture. To simulate the ignition delay time, we use a 0D closed homogeneous reactor model, which is included in the software ChemKing Pro. To run a simulation, we have to provide some inputs as initial temperature, pressure, fuel gas mixture, and RCM volume profile to take into account the heat loss during the piston movement. The most important part to run simulation is the kinetic model. This kinetic model has to describe the reaction involved during the experiment. The kinetic model of this study consists of two parts. One part represents the surrogate fuel chemistry and the other part describes the ferrocene chemistry. The surrogate fuel submechanism is adopted from the model of Lawrence Livermore laboratory, which contains the reaction of the toluene and N-heptene. In addition, we have updated some reaction of aromatic compounds, including toluene and cyclopentadiene, thanks to the recent data in the literature. The ferrocene submechanism is developed principally based on the work of Fernac and co-worker. The mechanism of Fernac and co-worker contains three main parts. The first one is the decomposition of ferrocene, and the second one is the reaction of ferrocene with radicals, and the third one is the reaction of iron compounds. To complete the reaction of iron species, we add in the model some additional reaction considering iron gas phase chemistry found in the literature. We suppose here ferrocene show a homogeneous effect, so we eliminate the heterogeneous reaction of iron peroxide. Here I present to you the result of my study. The figure presents the ignition delay time as a function of the inverse of temperature. For the surrogate fuel, first stage ignition were observed at temperature smaller than 745 Kelvin. Moreover, negative coefficient temperature phenomena were observed in the range of temperature between 745 and 850 Kelvin. It was experimentally found that ferrocene increased the main ignition delay time of the surrogate fuel at temperature higher than 800 Kelvin. In simulations, the model failed to capture the inhibiting effect of ferrocene. Considering the simulation and condition in which the effect of ferrocene is significant, we found that the effect of this additive could link to three species, which are ferrocene, iron monocyclopentadiene, iron dihydroxide, which are principally formed during combustion phase of a RCM experiment. By brute force analysis, we found that the reaction of ferrocene with peroxides are sensible to represent the effect of ferrocene at temperature smaller than 850 Kelvin. At temperature higher than 850 Kelvin, it was found that the reaction of iron dihydroxide with reactive radicals such as hydrosol, methyl, ethyl, or benzo are responsible to simulate the inhibiting effect of ferrocene. By adopting rate constants which were optimized manually, the actual kinetic model is capable of simulate reasonably the inhibiting effect of ferrocene in the whole examined temperature at two considered equivalent ratio. Thanks to the validated submechanism of ferrocene, we examine the different chemical effects between ferrocene and 2-ethyl hexanitrate, which is a conventional system booster. This additive has been previously studied in our last work, and for short, I call 2-ethyl hexonitrate as EHN. I show here the figure presenting the ignition delay time as a function of inverse of temperature of the next surrogate fuel and fuel doped with EHN and ferrocene. Experiments were conducted in RCM at 10 bars for stoichiometric mixture. Different from ferrocene, EHN reduced the ignition delay time of the surrogate fuel. The most two remarkable differences between two additives are how they affect the surrogate reactivity at low temperature range and at NTC zone. While toluene chemistry governs the surrogate fuel reactivity at low temperature range, and heptene chemistry relates to the NTC phenomenon of the surrogate fuel. Toluene, by the initiation step, forms principally benzyl radical. Then benzyl radical form benzyl peroxide radical by an addition with oxygen. Ferrocene deactivates benzyl peroxide radical by transforming it into stable alcohol. Conversely, NO2 formed due to EHN decomposition react with benzyl and produce benzosine radical, which is more reactive than benzyl peroxide radical. NTC phenomenon is governed by the release of HO2 from N-heptyl peroxide radical. In presence of EHN, NO transforms N-heptyl peroxide radical into heptoxy radical, which are more reactive. Due to this, the NTC phenomenon is mitigated by EHN. In presence of ferrocene, this additive converts HO2 into stable molecule. This accelerates the decomposition of N-heptyl peroxide radical, favoring NTC phenomenon. I finished my presentation by resuming some important points. The goal of my work is to investigate the chemical effect of an octane booster named ferrocene in a low-octane gasoline fuel. The measurement of ignition delay time of fuel were conducted in a rapid compression machine in a low temperature range from 675 to 1000 Kelvin under lean and stoichiometric conditions. The experimental result was simulated in a 0D reactor model. By experiment, we found that ferrocene increased ignition delay time. This effect increased with temperature. The effect of ferrocene is reasonably simulated by the kinetic model developed in this study. Thanks to the kinetic model, we investigated the chemical effect of ferrocene. The inhibiting homogeneous effect of ferrocene is linked to the deactivation of reactive radical, especially peroxide radicals. We also presented the difference in chemical effect of ferrocene with EHN on NTC phenomenon and on aromatic reactivity. In conclusion, this work presents a validated ferrocene kinetic model. This work contributes also to the understanding chemical effect of conventional fuel additive at engine-relevant conditions. These results would contribute to the design of new generation of fuel additive. Thank you for your attention.